here. Right. So when we put this together the first time around last year, RNNs were kind of going out of fashion, or in the process of going out of fashion. I will talk about why that is the case, and Nick is going to talk about the sort of next generation architecture that's replacing RNNs in many use cases. And this year, it's not like they are in the process of going out of fashion, they have kind of gone out of fashion. So we used to have, or last year we had 2 lectures on RNNs, and this year we've compressed it into just 1 lecture so that you don't, come with your pitchforks and say, why have we spent 2 lectures worth on something that's not even used these days in deep learning? But I think it's still something that has contributed to a lot of success stories in the mid 2010s. So 2015, 2016, I think was the time for the recurrent neural networks. And I think it's also useful to illustrate some ideas that are generally applicable in a lot of other deep learning situations. Okay, so RNNs are a little bit different from what we've seen before, or what we've shown you before. You have seen fully connected neural networks, the multi-layer perceptron that I had on my slides every once in a while. And then Nick has talked about convolutional neural networks, which also had this structure, which is generally referred to as feed-forward neural networks. So you have some kind of input like an image, and then there are layers of computation that feed into each other, and then at the end, something comes out, typically like a prediction about a class or something else. RNNs are different in that they operate in a different input type, and typically RNNs operate on sequences of data, which can include text typically, but I'm going to show you other examples of sequential data. And they're also very quirky in that people have come up with like very unique and very recognizably RNN. How do I make this disappear?
You can drag it.
Drag it to the bottom. Is this better? I don't know. Anyway, so the people have also come up with some very quirky building blocks, and some of this was a necessity to make them work. We will see that things like gating mechanisms and multiplicative interactions, I'll explain what these are, have been pretty crucial in making this idea work in practice, and actually not, to be able to train them on realistic data. And people have come up with all sorts of other tricks to make them work for longer sequences, such as skip connections and things like that. So it's a very fertile ground for people coming up with all sorts of random things that then turned out to be very useful, like architecture design-wise for neural networks. And today's lecture, I'm also going to talk about a different objective function, a different thing that we are going to do with these neural networks. I will briefly talk about maximum likelihood. How can you use neural networks for maximum likelihood density estimation or estimation of a probability distribution, and how you can use these methods for generative modeling. So rather than take a piece of data and predict a class or a label, we are going to build, or we are going to talk about models that can generate random data. They see a ton of different data, like a lot of different text, and then we train the method to be able to generate further random examples of text. I just come up with random text on its own. So that's going to be a new use case that we will talk about, that RNNs are very well suited for. So modeling sequences, I'm going to use this notation hopefully consistently. The inputs to the network is changes as time goes on. So time step 1, I'm going to call it x1, and then it's x2, and then xt. I think, just think of these as different characters from a string, for example. RNNs are in theory capable of modeling sequences of varying length. That's, I think, a big advantage, or that used to be a big advantage of them. Convolutions usually work with a fixed size image. It's very difficult to evaluate them when you have different size images. But RNNs technically can handle that. Sometimes we think of the strings as containing an end of string symbol at the end. That's very straightforward. And we can use them for a bunch of things like sequence classification. Here's a piece of text, determine whether it is hate speech or not, for example, is an example that you can use them for. You can generate sequences, for example, language generation, or you can turn sequences to other sequences, like in translation. You take a German sentence and spit out the English translation of that sentence. The typical diagram that we kind of used to draw about RNNs looks like this. So at the bottom, we have the data, the input data X. I use this notation to say that this is kind of indexed by time and it runs from 1 to t. And then we have from bottom to top, we have the different layers of this neural network. And what you will see is that there are these recurrent connections. And what this means is that when I, these hidden, these layers of the network now have a hidden state, or they have a state of their own called H1 for the first hidden layer. And in order to calculate the hidden state in the next step, I'm going to use the input from the previous layer, which is X, and I'm going to use the hidden state from the previous time step as well. This is what the red arrow, circular arrow is supposed to show here. So this unit here, or this kind of box, has an internal hidden state, and because it uses its previous hidden state to update its hidden state, it has a memory. It can kind of remember some aspects of the sequence as it's processing the data. And then subsequent layers of operation work similarly, except that they take the hidden state of the previous layer, or the layer below it, as if it was the input, and that's what it keeps integrating that information in itself. And then at the end or top of the network, we produce potentially some sort of output sequence Y1 to T. And I think over time, we switched from drawing RNNs in this way, because it's very ambiguous what these circular arrows mean, to drawing the computational graph unrolled in time. So in this way of drawing things, time goes from left to right. You can see X1, X2, X3, all the way to XT at the bottom. And these boxes are now copied over for each time step. So within the same row, it's the same nonlinear computation that happens at every time step. So all of these boxes in the same row are carrying out the same computation. And each of these boxes takes the input from the current time step and the output of that same box from the previous time step. That's what the horizontal arrows are showing. And then the output of this computation is passed on to the layer above, and it's also passed on to the next time step. So you can think of these networks as being deep both in the usual way from where your inputs are to where your outputs are. There are layers of calculation between X and Y, but it's also in a way deep if you look at it horizontally, because you're kind of applying layers of computation, because every time step you apply some nonlinear computation to your hidden states. Now, RNNs can be used in multiple different ways, depending on how exactly you use the inputs and the outputs of the network. The simplest one on the left is actually the feed-forward one. There is no time recurrence here. So you just have one input, the red one, and then some kind of computation, and then it produces an output, which is the blue rectangle. You can use RNNs in a one-to-many situation where you have a single input, for example, an image, and then you use the RNN to generate a sequence of outputs. So this can be, for example, describing an image using text. You would use an RNN in this fashion. So the input doesn't change over time, it's a fixed image, but the output keeps producing characters, the next character of a string that maybe describes the image. Similarly, you can do many to one. So your input might be a sequence like text, and your output might be a single scalar like a classification score or something like that. And then there are different ways to use RNNs when you map sequences to sequences. This one here, the fourth one, is sometimes called sequence to sequence. So when you hear seq to seq or sequence to sequence, people typically think of an architecture that looks like this. So what's happening here is that you have your input sequence, the red rectangles. These are, for example, the characters. It gets incorporated into the hidden states of the network, but you don't generate any output until the input sequence ends, and then you start generating the output. Once the input sequence is over, now you start generating your output. Or you can use it in this fashion where, as I showed you before, you simultaneously consume each character of the input and then produce the character of the output. Can anyone guess why this fourth one, where you wait until you've consumed the whole of the input sequence before you generate the output sequence, why that would be advantageous, or in what situations would this be a better way of using RNNs? Yes? Machine translation, yes. So, and can you tell me why?
Because like not all languages have the same sentence structure, so some might have like the verb at the end of a different word or the
Yeah, exactly. So because not all languages have the same sentence structures, there's usually not a one-to-one mapping between a character of the German sentence and the corresponding character of the English sentence. So in a German sentence, for example, sometimes the verb ends, the sentence ends with the verb, so you have to wait all the way until the end of the German sentence to know what the second word is that you have to produce in the English translation. So you kind of have to, you can't start translating the English sentence until you've seen the whole of the German sentence. All right. As I said, one of the things that we used RNNs for is generating sequences, and I will show you how that's done. The goal is to model the probability distribution of sequences. And here, the probability of a sequence is the joint probability of this particular sequence of characters. And with RNNs, we typically decompose this or model this probability distribution using the chain rule of probabilities. And we model the generative process of generating a sentence as a one step at a time process. So we generate for example, each character given the previous characters you've already generated. So here, the probability of a sentence is going to be the probability of the first character being x1 times the probability of the second character being x2 given the first character being x1, it's not shown here, and all the way up to generating the last character given all the characters that we've generated so far. The reason why this decomposition is helpful is because, for example, if you think about sentences, they are very, very high dimensional complicated objects. Even if you just have an alphabet of 30 characters, a sentence of, I don't know, 10 characters long ends up being, there's too many possibilities, too many different sentences, the probability of which you want to model. Whereas here, these individual conditional probabilities of the next character given the previous character sets only need to define a probability distribution over a single character, given what you've seen so far. So these objects individually that appear in this product are much, much simpler objects in a way to model with a neural network. And this is why this decomposition makes a lot of sense. And it also maps very well to this one step at a time kind of processing style of the recurrent neural networks. And that's what is shown here. So the way you would use an RNN to model this product to model this distribution over sequences is to first don't give it any input and just, you know, with an empty input, generate the first output, and you interpret that first output as being a probability distribution over characters. Let's say that the probability distribution over characters is such that capital T is the most likely character, which is actually quite likely because most sentences start with the. And so once you can then sample from this probability distribution, and you can sample the first character of your sentence. And then once you see the actual first character of your sentence, you can feed that into the RNN. It's going to, you know, continue processing it, incorporating the previous hidden states, and it's going to produce another output which you now interpret as a probability distribution over the second character. And it's now going to be conditioned on the first character because at this point, the RNN has already seen the first character. And then so on. Once you see the second character, you can incorporate that into the hidden states, and the output produces for you something that you can interpret as the probability distribution of the third character given the first two. So this is how you would use an RNN to define these probability distributions, which you can then multiply to evaluate the probability of this entire sentence or this entire sequence x1, x2, x3, all the way to xt. The way you would train this is this. So let's say that I observe some specific piece of text that is in my training corpus, and I want my the distribution that's defined by this neural network to be more likely to produce text like the one that appears in my training corpus. The way I would do that is by using a loss function, which would look like this. I take my prediction, this distribution of what the first character might be. I take the actual first character from the sentence, x1, and then I evaluate the log probability of this character under this distribution. So if it's a capital T, for example, I might have a high value here. If it's a weird character that's very unlikely to be a first character, or we predict that it's not going to be the first character, I might get a lower value here. Then I take the predicted distribution for the second character and I compare it. I evaluate that predicted distribution at the actually observed second character x2, again by evaluating the log probability of x2 under this distribution that my network outputs. And if I take all of these log probabilities and sum them up, because previously here we had a product, if you take the logarithm of this whole equation, then everything the product turns into sums under the logarithm. This is why we take the log here. So we can just sum these values together. At the end, I'm going to have the log likelihood of my sentence, which is the log probability of this entire sequence being generated by the product of these conditional distributions. And then I can just do backpropagation, trying to make this log likelihood as large as possible or as high as possible. And of course, at the bottom, I'm still feeding in the characters so that it knows when it's predicting the second character, it knows what the first character was and so on. So this part at the top is part of the loss function, and the bottom part is the RNN that's making these character predictions. What do I do once I've trained this model? So let's say that I run backpropagation, I update the parameters of this network, and it's going to get better and better at predicting the next character. How do I use my trained network? Here's how I would sample a new random sentence from my trained RNN. I would again start from an empty hidden state, generate or get a probability distribution of the first character, and I randomly draw the first character from this probability distribution. And then I'm going to say, okay, I stick to this. This is going to be my first character, and I'm going to feed it back to the RNN. Now this is my first character. Predict me what the second character should look like. So it's going to make the prediction of the second character. You can sample randomly from that probability distribution that gives me x2, and so on. You kind of feed the output of the RNN back to itself in this fashion. This is how you would use an RNN to generate random sentences. They're going to be random sentences because every time you generate the next token, you draw from this random distribution. And this is more of a history lesson at this point. This is from 2015. When people first applied these neural networks, first applied these neural networks in the modern deep learning frameworks so that they could experiment with various things and they could use large neural networks, we were very surprised at how well it actually works with relatively small amounts of training. So what you're looking at here is random text that has been generated by an RNN that was trained on character sequences, in this case, trained on some drama text. I don't actually know what the data set was specifically for this. And you can see that it probably like regurgitates a lot of the things that it's seen in the training data, but that it also does things that are kind of random. If you actually read this, you will notice that it's probably not something that was copied directly from the training data set. And interestingly, it has also learned to respect the structure of this text overall. So it uses these white spaces and it uses the columns correctly and everything. This was really surprising that RNNs could do that at the time. And you can also feed this to other types of data set. This is when you feed it to Wikipedia, it produces this. It also produces, when you ask it to generate random Wikipedia articles, it's going to also generate this, random annotations and links in Wikipedia style. You can also feed it to XML data, and it's going to generate, again, this is just character by character, and it actually generates XML that compiles, or not doesn't compile, but it sort of checks out, the syntax checks out. With certain probability it won't work, but it is surprising enough that sometimes it does work. And this is an example where he trained it on LaTeX documents, the source code of LaTeX documents, and then you generate a random thing from the RNN, and then you try to compile it with LaTeX, and it actually compiles some of the time. And this is the sort of thing that you get when you do that. You can see that there are like lemmas and proofs and things like that. I haven't checked the details, but I don't think that it makes any sense. It just sort of respects the texture of what math is supposed to look like, kind of. We've gotten a lot better at generating text. I mean, a lot of you have probably, if you've been following machine learning, none of this is going to be surprising to you. And you will know that there are much, much better text generation methods out there. But I just showed these examples because in 2015, this was actually very, very surprising to a lot of us in the community that it works so remarkably well. But it wasn't that easy in the sense that when Andrej created these examples for the blog post, he didn't just use the vanilla or an arbitrary version of an RNN. He used very specific versions of the RNN, which I'm going to talk about. One of the problems with this RNN is that they forget too quickly, by which, in a very specific way, which means that as it's processing data, what the first input token was, it stores that information in the hidden state. And as it's processing more and more of the input sequence, the influence of that first character over time easily vanishes, so that it doesn't, it should kind of remember in its hidden state what the first character was, but in practice, unless you're very, very careful, as you're applying these recursive operations on the hidden state, that information about what the beginning of the sequence was very, very easily gets lost. And in mathematical terms, this manifests itself in either of these two problems. One of them is a vanishing gradients problem, which means that the gradient of the network's output with respect to, say, the first character vanishes, which means that it becomes exponentially small, or in the opposite case, it might explode, in which case the first character will have a huge influence on the output of the network and nothing else. You know, once you've seen the first character, that kind of predetermines what the network's final output is going to be. So why does that happen? Let's look at the, let's try to actually look inside those boxes and think about what we would put there. And one of the natural choices of what to put there would be to try to replicate the multi-layer perceptron. Remember that the multi-layer perceptron, each layer of it took the previous layer or the input to the network. It applied a linear a matrix multiplication, and then it applied a nonlinearity which acted component-wise on the vector. So this is now a box which has two inputs. It has the input xt, but it also has the hidden state ht from the previous time step. So it makes sense to generalize that idea by saying, I'm going to take these two inputs, I'm going to first apply a linear operation, multiply each of them with some parameters, wh and wx, and then maybe add some bias term, and then I'm going to apply this, this nonlinearity. So this would be the straightforward generalization of the multilayer perceptron to the recurrent neural network idea, or recurrent neural network structure. And then the final output of the network would just be take the, say, the final hidden state ht at time t, again, apply a linear operation here, a matrix multiplication plus an addition, and then apply some nonlinearity, you know, for example, to make this output a probability, if that's what you wanted to output. Now, what would be a problem with this setup? The problem is that we are going to apply the same matrix over and over again as we are recursively applying this formula. So when I'm calculating ht plus 1 from ht, I'm using this wh matrix. And when I'm calculating ht plus 2 from ht plus 1, I'm using that wh matrix again. And this is the sort of problem that's going to be caused. This goes back to the backpropagation / automatic differentiation lecture. So we can look at what the derivative of the loss, L hat, is going to be with respect to the network's hidden state at time t. And this decomposes using the chain rule into the loss derivative of the loss with respect to the final hidden state, H capital T, and then times the derivative of the final hidden state with respect to the hidden state at the penultimate step, and so on. So you can kind of walk your way backwards in time. This is also sometimes called backpropagation through time, because here this backpropagation or automatic differentiation happens walking backwards in time, basically. So you have these Jacobians, a product of Jacobians appearing here, which is always the derivative of the next times hidden state with respect to the current hidden state. And if you write it out in this particular vanilla RNN architecture, what you're going to find is that every time that this gradient is calculated, you're going to have a term that is WH here, that is for the linear operation. And then you are going to have this a diagonal matrix diagonal matrix DS, which I have it written down here, is the gradients of the nonlinearity at that particular point in time. And this is this DS is a diagonal matrix here. And if sigma is chosen to be the value, then we know that the derivative is going to be, the derivative of the value is either 0 in the flat region or it's 1 in the linear region. So we know that this diagonal matrix dt or ds for in time step s is going to be a big diagonal matrix where the diagonals are either 0 or 1. So it's a very simple object. So most of the interesting complexity here comes from WH. And this WH appears capital T minus T times. And if the length of the sequence is growing, so capital T grows, and say small t is small, so you're looking at the beginning of the sequence, you're going to be looking at this WH raised to potentially a very high power. So if it's a long sentence like 100 characters long, then and small t that you're looking at is 0, then this is going to be this matrix raised to the power of 100. And this is what the gradient looks like. And the problem is that when you if you consider this W just being a constant, and what happens, so not a matrix, just a single scalar, if you raise it to the power of 100, the 100th power, if that scalar happens to be 1, that's fine because you just end up with a, if you raise it to the power of 100, you end up with 1. If it's bigger than 1, then raising it to the power of 100 makes it a very, very large number. If it's smaller than 1, then raising it to the power of 100 makes it a very, very small number. So the gradient, if this W is not 1, if it was a scalar, would be either very small or would be exponentially big. This is sort of the vanishing or exploding gradients problem that we are talking about. Now with matrices, what determines whether this is going to be very big or very small are the eigenvalues of this matrix. So if you might recall from your linear algebra that if this matrix is such that all the eigenvalues are smaller than 1, then it means that when you apply this matrix to a vector, you multiply a vector by it, then the size of that vector decreases. So it's basically shrinking. And when the eigenvalues are larger than 1, then the size of the vector increases. So depending on the eigenvalues of this matrix, this can either explode or go to 0, or typically what happens is that selectively along some dimensions it goes to infinity and some other dimensions it goes to 0. So your gradients are going to be very poorly behaved. And yeah, this is just saying the same thing, but with a little bit of math. So how can we fix this problem? I like this way of fixing the problem from 2016. It's not a particularly popular paper. I don't think that many people use this technique, but I like to talk about this because it's, I think it really went to the heart of the problem and proposed a solution that's mathematically very elegant. What they basically do is they force the weight vectors in RNNs to always have eigenvalues of 1. So they always use unitary weight matrices. Unitary matrices are those that have eigenvalues of 1. And this basically ensures that the gradients neither explode or vanish. And if you restrict your weight matrices in such a fashion, then indeed you can sidestep this problem of vanishing or exploding gradients, and this method works reasonably well. A more typical solution that's, in my opinion, maybe a little bit less elegant, on the other hand, it's used a lot in actual machine learning, is to rely on gating mechanisms. So up here I have the vanilla recurrent neural network again, and below I have the equations that describe the hidden state evolution of the gated recurrent unit. And you can see that it doesn't just have one hidden state H. It actually has an intermediate hidden state H tilde, and it has R and it has Z. And what the function of these R's and Z's are going to be is to control the information flow from the previous step to the next step. So for example, look at this, the top line of the equation. And I'm not going to go through all of these equations. I recommend that if you're interested, just look at what it's doing and try to disentangle what the meaning of these operations are. But let's just look at the first line. What it's doing is if, when I'm calculating the next hidden state, if ZT is 1, this is a component-wise product, this circle dot with the circle around it. When ZT is 1, I'm basically going to copy over the hidden state from the previous step without modification. If ZT is 0, then I'm going to use the second term. Then I'm going to update my hidden state completely to this new state called H tilde. So Z allows me to, the value of Z itself is determined by the neural network using this equation down here. But this unit kind of has this ability to determine whether to completely ignore any new information in this time step by setting the ZT values to 1, or to completely ignore the current hidden state and completely forget the previous hidden state and only pay attention to the new information. So it can basically forget all the old information, and it can decide to ignore the current information that it receives. And the diagram that people draw to illustrate what this looks like is like this. These Z's and these R's in the equation are called gates because they control the flow of information in this computational graph. Notice though that everything here, even though these switches look like they are discrete objects that you can flip between two positions, in reality they are continuous switches, so they are all still differentiable. They don't actually take the value of 1 or 0. They can take values in between, in which case you can have like interesting, averaging behavior between these two things. But once you introduce these gates, it solves the vanishing gradient problems, and it gives the network this flexible ability to decide which information to remember and which information to forget based on the information itself. Now, this is again history. LSTMs have a LSTMs are something that's even more complicated than GRUs, gated recurrent units. It has even more moving parts. You can look it up on Wikipedia, I guess, or many other places. There's going to be a ton of blog posts about it. It was invented in the 90s by Hochreiter and Schmidt-Huber, and it has contributed to a lot of breakthroughs in first handwriting recognition, but then more importantly in speech and text processing. Neural machine translation being kind of I think the flagship application that RNNs really nailed in 2016. But RNNs aren't just for text. I'm just going to flip through a couple examples of recurrent neural networks being used for applications that you maybe wouldn't expect something like this would be used for. So here, this is a method for generating images by decomposing the image generation process into a sequence of operations. And what these red squares are showing, red squares here are showing is that this neural network has a hidden state that is where it's looking at in the image, or which part of the image it's currently generating. And then within that scope, it's allowed to modify the image slightly. And then each step of the RNN, it can update where it's looking at within the image, and it can change the image locally in that region. This is also something kind of cool where you actually hook this RNN up with something like Microsoft Paint or like a simple painting software or drawing software. So This RNN is allowed to make brush strokes with different brushes, with different colors. And you can see the sequences of brush strokes that it applies. And it's trained to produce images that approximate human faces. And you can see that it learns to kind of draw something that looks vaguely like a face. And you can see what it's producing. You can also make them reproduce a specific image. So for example, here's an input face, and it then tries to reproduce them with a certain number of brush strokes that it can do. And the interesting thing with this particular method was that if you really restrict the network's ability of how many steps it can use, like how many different brush strokes it can use, then these very abstract drawings emerge from it. Like, you know, how can you draw a face with only 5 brush strokes or something like that? This is kind of the network's answer that it learned to do. Another way to apply RNNs to images is by generalizing the computational graph to more of a 3-dimensional structure. So LSTMs or RNNs had this 2-dimensional computational graph because there was the time aspect to them, and then there was a depth aspect. If you apply them to images, so this would be an image down here, then you would have the two dimensions of the image, horizontal and vertical pixel position, and then you would have the 3rd dimension, which is the depth of the network. And if you can make each of these units work the same way as the RNN units are working, like LSTM units, and then you can start modeling images with LSTMs. And these are some examples of textures that were generated using the spatial LSTM architecture. One thing that has been particularly successful, and I've already talked about this a little bit, is this sequence-to-sequence architecture, where you first consume some input sequence. The hidden states are going to capture, if you apply this text, the meaning of the text. I think this hidden state was called the, was it the meaning vector? Jeff Hinton called it. Anyway, or thought vector, that's the one. So it's sort of what the network is thinking after reading, say, the sentence, and then initializing another RNN from this thought vector, it then starts producing output. And this sequence-to-sequence method had several years of high productivity, and in particular, neural machine translation has been one of the flagship achievements of with this architecture. As I said, you can also use this architecture in combination with other things like CNNs. You can, for example, make the input an image and make the output some text. And so image-to-seq does this. It generates the text description of a particular image shown on the left. And this has worked also remarkably well. Now we have way better examples of this that are not using RNNs. But you can also see, if you look at these slides at home, you will find some very funny examples of where it's going wrong. You can also use them to turn sequences into graphs. The seek-to-tree generates a parse tree for a sequence given the input sequence or input sentence. You can see that, in fact, it's generating this parenthesized description of this tree. And this exploits the fact that RNNs are very good at learning this sort of syntactic structures. You can use RNNs to perform all kinds of interesting algorithmic problems. So in this case, the traveling salesman problem. You give the RNN a sequence of points. In fact, this is a set of points. And then it spits out a sequence that solves approximately the traveling salesman problem. So at training time, you show it several examples of here's a set of points, here's the solution to the traveling salesman problem, and then it's going to be able to generalize to even larger point sets and do really well. You can use the same methods to find the convex hull of a set of points, like is shown here on the left, or the triangulation of given a set of points, what's the optimal triangulation of these points. If you've done some 3D rendering, you might be, or finite element methods, you might be interested in this sort of thing. So, so it's been applied to a number of different things, but it had a drawback, which is the seek-to-seek architecture, and that's the fact that all the communication, so to speak, between the input sequence, say the German sentence, and the output sequence, which is the English sentence that it needs to generate, happens through this bottleneck, the thought vector. So it has to remember everything about the input to be able to generate the output. And if you imagine translating a sentence, that's actually a very, very difficult task. If you have a long and complicated sentence, to first read it, remember it, and then you're not allowed to look at it, and then you have to reproduce it in another language. That's a much more difficult way of translating than we usually translate sentences. We usually translate by, constantly looking at the input sentence as we are doing the translation. So in order to solve this problem, people have come up with something that mimics this process that humans do, that they are allowed to pay attention to different parts of the sentence, of the source sentence, as they are creating the translation. I'm not going to talk about this too much because Nick is going to talk about this in the next lecture. This is called the attention mechanism. But roughly the idea here is that as you are, this is the input sentence, source text, and this is probably summary generation here. So when you are generating, say, the second word of the output, you are creating a context vector that allows you to look back at the inputs. These are the sort of the hidden RNN hidden states as the network was processing the input. And as you are here, you're allowed to look back at certain locations of the input. And what happens is that you generate these things called attention weights, which is how much attention the network at this point wants to pay to certain time steps in processing the input. So for example, you can see that it's generated Germany beat, and it probably now wants to say which other country did Germany beat. So it generated an attention distribution that actually correctly focuses on the country that it was playing against, Argentina. And so these blue bars show the amount of attention it's paying to certain parts of the input. Now this had allowed RNNs to even further increase their performance on a lot of different text modeling tasks. It was really a very influential idea. And it turned out that it was such an influential idea that eventually the idea itself killed RNNs completely. What turned out to be the case is that people found out that once you introduce this attention mechanism, once you introduce this ability for the network to pay attention to different parts of the input sequence, the recurrent neural network processing bit was completely unnecessary. So if you go back to this graph and if you keep this attention part at the top, which we just introduced, and you completely cut these arrows, this is, by the way, a bidirectional RNN, which goes both forward and backward in time. But if you cut these recurrent connections completely from the network, it would still work just as fine, and it would still be able to do, solve the tasks just as accurately as the RNN plus the attention. So attention was introduced to make RNNs more powerful, but in the end, they caused the downfall of RNNs. And so over the last couple of years, since 2017, I guess, more like 2018, RNNs have been going out of fashion, and they have been replaced by just purely attention-based methods, which are also called transformers. So if you have heard about transformers in the context of machine learning, of course, then they are essentially architectures that make use of this attention mechanism that Nick's going to talk about tomorrow. And they are kind of the next generation architecture that almost made RNNs obsolete for most of the modern machine learning tasks that we do today. So that's what I wanted to talk about RNNs. If you have any questions, I'm happy to answer them. I'll stop the recording.